Okay, let's ask some sort of silly sounding questions that really do need to be asked and really do need to be addressed. Does 3 have 3 elements? So you could say, well, 3 is this set. This is consisting of 0, 1, and 2. And look, that's 3 things. I can count them. It has 3 elements. 1, 2, 3. Well, that sounds sensible, but pointing with your finger at marks on a chalkboard is not a proof, right? A proof is a sequence of propositions that relies on the definitions and the previously proven theorems and the rules of logic to establish other propositions. So if I really want to prove that 3 has 3 elements, I do have to use the definition of has 3 elements. So let's write this a little bit more clearly. 3 has 3 elements means that, right? So that's the question. To say A has n elements is just to say that n is a natural number and A has the same cardinality as n. So 3 has 3 elements means 3 is a natural number, well, we know that, and 3 has the same cardinality as 3. So this is the question. And the answer is yes, because, for example, the identity on 3 is a map from 3 to 3, which is bijective. It's not the only map 3 to 3 which is bijective, but it's the easiest one to write down at this moment. Okay, great. 3 has 3 elements. N has n elements. Does 3 have 4 elements? So just because I've proven 3 has 3 elements, that doesn't mean 3 cannot also have 4 elements. 3 has 4 elements means 3 is in bijection or has the same cardinality as 4. This is a little bit more difficult, actually. So I know there exists a bijection from 3 to 3, like here's one, the identity on 3, but how do I know there doesn't also exist a bijection from 3 to 4, or bijection from 4 to 3? How do I know that? So the answer is no, but why not? So this goes back to the, I guess the first video of this series of coronavirus videos, where we were drawing pictures and we were like, well, if you're going to have a surjection from 3 to 4, then 4 had better have at least as many elements as 3. And we just don't think there are enough dots in the diagram. This has 3 dots in its diagram. This would have 4 dots in its diagram. There doesn't seem to be enough to get a surjection from here to there. There doesn't seem to be enough to get an injection from there to here. So whether you're talking about 3 having 4 elements or 4 having 3 elements, it seems just a bijection is not possible because in the picture there's different numbers of dots and you can't connect the edges to get everything to be bijective. But the picture is not a proof, so we still ask, why not? And here's the more general question. It shouldn't just be about 4. If 3 has n elements, does that mean n is 3? Is n equals 3 the only number for which 3 has that number of elements? Okay, if this discussion is confusing, why these are even questions, how this is not just trivially following from the words that I'm using, if this is confusing, then you have to go back and look at how the words were defined. How is has 3 elements defined? That is defined in definition 120, part 1. So has 3 elements is defined in 120, part 1. And yeah, it's just not necessarily trivial. Well, this one ends up being, but answering these is not necessarily trivial. Okay, so here's something that kind of gets at the heart of the matter, I think. Suppose n and m are 2 natural numbers. Then we have two kind of things that look like a less than symbol. There's the curvy looking less than symbol, which stands for there exists an injection from n to n. And then there's the straight looking less than symbol, less than or equal to, which stands for n is less than or equal to n. Less than meaning membership, right? So this was the one from our section on natural numbers. So this less than or equal to means member or equal to. This one means there exists an injection. But we really think of both of them as saying that, this one we think of as saying that in the ordering, in terms of succession, in terms of one natural number being the next of another, which is the next of another, which is the next of another, this means that in that ordering, m comes after n, or is equal to n. This one is not really focusing on the ordering or the succession. It has nothing to do with next, and it has nothing to do with this necessarily. It has everything to do with the number of elements in each of these sets. So this is really all about being able to build an injection from n to m. It's really all about whether m has enough elements for it to be possible to inject n into it. So these really do, at first, talk about different things. But we would like to prove that they are the same. So that's not going to be trivial, and that's something we'll do next time, that they are the same. So that will be theorem 122. So that'll be next time. And if, similarly, we have these two ways of saying that n and m have the same number of elements. Well, this is saying n and m have the same number of elements in the sense of there exists a bijection. And this is saying n and m are the same number. So we'll also prove this. I think there will be a gap in that proof, but we will more or less prove this next time. And this will allow us to address, if I prove this, I mean prove the equivalence. This will allow us to address a silly sounding question like, does 3 have 4 elements? Then we would say, no, if 3 has n elements, n is 3, and 3 is not 4, because 3 is less than 4, then we have trichotomy for natural numbers. All right, so next time we'll do this, and that should be the end of the course.